This is a presentation on Direct Memory Access, or DMA, by Emmanuel Dupart, Chris Stevens, and Reed Yoshida. What exactly is DMA? Direct Memory Access is hardware within a computer system that allows certain other hardware subsystems to access main system memory, or RAM, independent of the Central Processing Unit, CPU, which frees up the CPU to process other requests. The CPU first initiates the transfer with the DMA, then the CPU does other operations while this transfer is in progress, and finally, it receives an interrupt from the DMA controller when the operation is complete. There are a number of advantages with using DMA. First, it offloads the input-output operations for the CPU. This means that the processor does not have to execute instructions in order to transfer data and is, therefore, not used for handling data transfer. This frees up the CPU for other processing activities. Second, it has high transfer rates and fewer CPU cycles for each transfer. We get a higher transfer rate because we avoid context switching or storing the state of a process or thread so that it can be restored and execution resumed from the same point later. And we get fewer CPU cycles for each transfer because we have data transfer being done in parallel. Third, we get lower power consumption. Fourth, we have direct memory access. And fifth, we have a minimization of latency, or the delay before a transfer of data begins right after the instruction has been sent. This reduces the amount of temporary storage or memory required on an input-output device. DMA does have a few disadvantages. It can lead to cache coherency problems. If a CPU is equipped with a cache and an external memory, then the data the DMA controller has access to, stored in RAM, may not be updated with the correct data stored in the cache. Synchronization mechanisms must be provided in order to avoid accessing non-updated information from RAM. Another disadvantage is DMA transfers does require a DMA controller in order to perform the specific operation, and therefore the complete system can potentially be more expensive.
Why use DMA? The first reason to use DMA is memory-to-memory copying moving of data within memory. Second, offloading expensive memory operations from the CPU to a dedicated DMA engine. Components that use DMA are disk drive controllers, graphics cards, network cards, sound cards, and intra-chip data transferring in a multi-core processor. This is an illustration of how the DMA works. First, the CPU sends instructions such as address and control over to the DMA. From there, the DMA requests transfer to memory. Then, data is transferred into memory. Once all the data is transferred into memory, acknowledgement is sent back to the DMA, and from there, the DMA sends an interrupt to the CPU when it is done. This slide shows basic code for the DMA. It shows the enabling of clock, creating, and resetting the DMA. It also shows the initialization of what channel the DMA is going to use and to send information. It also shows the initialization of the peripheral and memory source and address. At the very bottom, it shows the enabling of that the data is transferred and the DMA will send the interrupt back to the CPU. There was some code cut out of this slide, such as other initializations of other channels and the priority of what's being sent.